Maxwell's equations are a set of partial differential equations that, together with the Lorentz force law, form the foundation of classical electrodynamics, classical optics, and electric circuits. These areas of physics are the basis for all electric, optical, and radio technologies like power generation, electric motors, wireless communication, cameras, televisions, computers, etc. Maxwell's equations describe how electric and magnetic fields are generated by charges, currents, and changes of each other. One important consequence of the equations is that fluctuating electric and magnetic fields can propagate at the speed of light, and this electromagnetic radiation manifests itself in manifold ways from radio waves to light and X-gamma rays. The equations are named after the physicist and mathematician James Clerk Maxwell, who published an early form of the equations between 1861 and 1862, and first proposed that light is an electromagnetic phenomenon. The equations have two major variants. The microscopic set of Maxwell's equations uses total charge and total current, including the complicated charges and currents in materials at the atomic scale. The microscopic equations have universal applicability but may be infeasible to calculate with. The macroscopic set of Maxwell's equations defines two new auxiliary fields that describe the large-scale behavior of matter without having to consider atomic-scale details, but the use requires experimentally determining parameters that describe the electromagnetic response of materials phenomenologically. The term Maxwell's equations is often used for equivalent alternative formulations. Versions of Maxwell's equations based on the electric and magnetic potentials are preferred for explicitly solving the equations as a boundary value problem, analytical mechanics, or for use in quantum mechanics. The spacetime formulations are commonly used in high-energy and gravitational physics because they are manifestly compatible with special and general relativity. In fact, historically, Einstein developed special and general relativity to accommodate the absolute speed of light that drops out of the Maxwell equations, with the principle that only relative movement has physical consequences. Since the mid-20th century, it has been understood that Maxwell's equations are not exact but are a classical field theory approximation to the more accurate and fundamental theory of quantum electrodynamics. In many situations, though, deviations from Maxwell's equations are measurably small. Exceptions include non-classical light, photon-photon scattering, quantum optics, and many other phenomena related to photons or virtual photons. Conceptual descriptions. Gauss's law describes the relationship between a static electric field and the electric charges that cause it. The static electric field points away from positive charges and towards negative charges. In the field line description, electric field lines begin only at positive electric charges and end only at negative electric charges. Counting the number of field lines passing through a closed surface, therefore, yields the total charge enclosed by that surface divided by dielectricity of free space. More technically, it relates the electric flux through any hypothetical closed Gaussian surface to the enclosed electric charge. Gauss's law for magnetism. Gauss's law for magnetism states that there are no magnetic charges analogous to electric charges. Instead, a magnetic field due to materials is generated by configuration called a dipole. Magnetic dipoles are best represented as loops of current but resemble positive and negative magnetic charges, inseparably bound together, having no net magnetic charge. In terms of field lines, this equation states that magnetic field lines neither begin nor end but make loops or extend to infinity and back. In other words, any magnetic field line that that enters a given volume must somewhere exit that volume. Equivalent technical statement so that the sum total magnetic flux through any Gaussian surface is zero, or that the magnetic field is a solenoidal vector field. Faraday's law. The Maxwell-Faraday's equation version of Faraday's law describes how a time-varying magnetic field creates an electric field. This dynamically induced electric field has closed field lines just as the magnetic field, if not superposed by a static electric field. This aspect of electromagnetic induction is the operating principle behind many electric generators. For example, a rotating bar magnet creates a changing magnetic field, which in turn generates an electric field in a nearby wire. Ampere's law with Maxwell's addition. Ampere's law with Maxwell's addition states that magnetic fields can be generated in two ways: by electric current and by changing electric fields. Maxwell's addition to Ampere's law is particularly important. It makes the set of equations mathematically consistent for non-static fields, without changing the laws of Ampere and Gauss for static fields. However, as a consequence, it predicts that a changing magnetic field induces an electric field and vice versa. Therefore, these equations allow self-sustaining electromagnetic waves to travel through empty space. The speed calculated for electromagnetic waves, which could be predicted from experiments on charges and currents, exactly matches the speed of light. Indeed, light is one form of electromagnetic radiation. Maxwell understood the connection between electromagnetic waves and light in 1861, thereby unifying the theories of electromagnetism and optics. Solutions. Maxwell's equations are partial differential equations that relate the electric and magnetic fields to each other and to the electric charges and currents. Often, the charges and currents are themselves dependent on the electric and magnetic fields via the Lorentz force equation and the constitutive relations. These all form a set of coupled partial differential equations, which are often very difficult to solve. In fact, the solutions of these equations encompass all the diverse phenomena in the entire field of classical electromagnetism. A thorough discussion is far beyond the scope of the article, but some general notes follow. Like any differential equation, boundary conditions and initial conditions are necessarily for a unique solution. For example, even with no charges and no currents anywhere in space-time, many solutions to Maxwell's equations are possible. Not just the obvious solution E equals B equals 0. Another solution is E equals constant, B equals constant, while yet other solutions have electromagnetic waves filling space-time. In some cases, Maxwell's equations are solved through infinite space, and boundary conditions are given as asymptotic limits at infinity. In other cases, Maxwell's equations are solved in just a finite region of space, with appropriate boundary conditions on that region. For example, the boundary could be an artificial absorbing boundary representing the rest of the universe, or periodic boundary conditions, or the boundary conditions may describe the walls that isolate a small region from the outside world. Jeffermenko's equations are the explicit solution to Maxwell's equations for the electric and magnetic fields created by any given distribution of charges and currents. It assumes specific initial conditions to obtain the so-called retarded solution, where the only fields present are the ones created by the charges. Jeffermenko's equations are not so helpful in situations when the charges and currents are themselves affected by the fields they create. Numerical methods for differential equations can be used to approximately solve Maxwell's equations when an exact solution is impossible. These methods usually require a computer, and include the finite element method and finite difference time domain method. For more details, see computational electromagnetics. Maxwell's equations seem overdetermined, in that they involve 6 unknowns but 8 equations. This is related to a certain limited kind of redundancy in Maxwell's equations. It can be proven that any system satisfying Faraday's law and Ampere's law automatically also satisfies the 2 Gauss's laws, as long as the system's initial condition does. This explanation was first introduced by Julius Adam Stratton in 1941. Although it is possible to simply ignore the 2 Gauss's laws in a numerical algorithm, the imperfect precision of the calculations can lead to ever-increasing violations of those laws. By introducing dummy variables characterizing these violations, the 4 equations become not overdetermined after all. The resulting formulation can lead to more accurate algorithms that take all 4 laws into account. Limitations of the Maxwell equations as a theory of electromagnetism. While Maxwell's equations are extraordinarily successful at explaining and predicting a variety of phenomena, they are not exact, but approximations. In some special situations, they can be noticeably inaccurate. Examples include extremely strong fields and extremely short distances. Moreover, various phenomena occur in the world even though Maxwell's equations predict them to be impossible, such as non-classical light and quantum entanglement of electromagnetic fields. Finally, any phenomenon involving individual photons, such as the photoelectric effect, Planck's law, the Duane-Hunt law, single photon light detectors, etc., would be difficult or impossible to explain if Maxwell's equations were exactly true, as Maxwell's equations do not involve photons. For the most accurate predictions in all situations, Maxwell's equations have been superseded by quantum electrodynamics variations. Popular variations on the Maxwell equations as a classical theory of electromagnetic fields are relatively scarce because the standard equations have stood the test of time remarkably well. Magnetic monopolies. Maxwell's equations posit that there is electric charge but no magnetic charge in the universe. Indeed, magnetic charge has never been observed and may not exist. If they did exist, both Gauss's law for magnetism and Faraday's law would need to be modified, and the resulting 4 equations would be fully symmetric under the interchange of electric and magnetic fields. Historical publications. On Faraday's lines of force 1855-56, Maxwell's first paper, compiled by Blaise Labs Research. On physical lines of force 1861, Maxwell's 1861 paper describing magnetic lines of force, predecessor to 1873 treatise. James Clerk Maxwell, A Dynamical Theory of the Electromagnetic Field. Philosophical Transactions of the Royal Society of London 155, 459-512. A Dynamical Theory of the Electromagnetic Field 1865. Maxwell's 1865 paper describing his 20 equations. Link from Google Books. J. Clerk Maxwell, A Treatise on Electricity and Magnetism. Maxwell, J. C. A Treatise on Electricity and Magnetism, Volume 1, 1873. Posner Memorial Collection, Carnegie Mellon University. Maxwell, J. C. A Treatise on Electricity and Magnetism, Volume 2, 1873. Posner Memorial Collection, Carnegie Mellon University. The Developments Before Relativity, Joseph Lama, on A Dynamical Theory of the Electric and Luminiferous Medium. Phil. Trans. Roy. Soc. 190, 205-300. Hendrik Lorentz, Simplified Theory of Electrical and Optical Phenomena in Moving Systems, propagate, Science Amsterdam, I. 427-43. Hendrik Lorentz, Electromagnetic Phenomena in a System Moving with Any Velocity Less Than That of Light, propagate, Science Amsterdam, IV. 669-78. Henry Poincaré, La théorie de Lorentz et le principe de réaction, Archives néerlandaises, v. 253-78. Henry Poincaré, La science et hypothèse. Henry Poincaré, sur la dynamique de l'électron, Comptes rendus de l'Académie des sciences, 140, 1504-8. Cat Walton and Davidson. The History of Displacement Current. Wireless World, March 1979.